In the next two sections, we'll make further use of the duality theory in approximation algorithms. And the first one, so there's two separate techniques. The first one is called dual fitting, which is, if you want, rather an analysis technique that uses duality as opposed to an algorithm that directly uses it. And we'll see that on the example of set cover as in the past. The basic idea is this, that we have some algorithm. Often it's an algorithm that already existed before we even thought about duality. And the algorithm maintains a candidate solution that is a feasible solution. So it's feasible for the ILP, I should say. It's integral and feasible for the primal solution. So in set cover, it has to be a set cover. But then, or at the end at least, it has to be a set cover. But the guarantee for its bound, we can analyze by taking the bound, the cost of x in the primal LP, and somehow derive from that a dual set of variables. They may not immediately be feasible, but we can modify this set of dual variables, or these values for the dual variables, by scaling them down, and then that scaled down version is feasible. And so you can use this as follows. The optimal actual value is what you're looking for. That's where we're still in this realm of doing the minimization CTX subject to AX greater equal B, x greater equal 0. That's our primal LP, and here, of course, would be in n to the n. If you have the ILP, so opt denotes the optimal objective value of the integral, best integral solution. Since it's a minimization problem, that's only going to get better if you loosen the integrality constraints to be just x greater equal 0. Come on, we have this easy option, so let me just get the two LPs written up separately. So that's our ILP, and that's our primal LP. So the optimal objective value of this one is going to be better than this one. That's CT for some x star, whatever that is. And by strong duality, that's the same as BTY for some optimal dual variable. So the dual will be the will be this one, and then that's the optimal. You could say that's opt of the dual, and we'll make sure that our y, I know this is a bit abstract and unclear. It'll be more clear on the concrete example. You somehow get to these dual variables from your algorithm. And if you scale them down, if you divide them component-wise by some scalar delta, then that is a feasible, dually feasible solution, which means its objective value is going to be at least, at most the optimal value for that LP. So you can continue this inequality chain. And then, of course, you can pull this delta out. So if you rewrite this for your concrete solution, it's going to be still less than that's weak duality here. And here you get this BTY. If you pull delta to the other side, you get that this is at most delta times the optimal objective value. So you get an upper bound for how bad your cost for this algorithm will be. And it all depends on how much you have to scale down these dual variables to make them dually feasible. That's the key question you have to ask. And so on our concrete example, The set cover problem, you'll remember hopefully, is a collection of sets over some universe. And we'll heavily use this notation. V of E is the set of all indices of sets where this specific element of the universe occurs. So the notation is somehow suggesting that this has to do with graphs. And of course, if you think about the special case of set cover, where it's a vertex cover, the elements of the universe are the edges of a graph. And then V of E would just be all the endpoints of an edge, just the two vertices. But in general, for set cover, this could be a larger set, right? Then we can write the set cover ILP or LP as we want to minimize the total cost. We've seen this before. XJ encodes whether the set is chosen in the solution or not. And we think of this as being 0 or 1. In the LP, of course, it could be fractional. We multiply it with the cost of that set. What's the side condition? It has to be a set cover, which means we have a constraint for every element in the universe, and we sum over all the sets that contain this element, and then in total they have to cover it. And in the integral case, that's a set cover. In the fractional case, it's a fractional set cover. Okay. You can dualize the set cover LP. Then you get this one just by applying the rules or the intuition from last time. So you have some variables YE. And oftentimes, so the way to think about this is that you go from primal to dual mechanically. You just follow the rules. But then it often helps to take a step back and look and stare for a while at this dual LP and see if it tells you something intuitively, because often it does. We've seen for vertex cover, this was particularly clean in that it gave you just the maximum matching. Here for general set cover is a little less clean, maybe. You get something, you want to maximize some YEs, a value for each element of the universe. And what's the constraints? They say if you sum up all the elements in some specific set, then you can't exhaust the cost of that set. So you could, C could nicely stand for cost or for capacity. So you could say that the universe elements are some goods, and you want to pack as much of that good as you can. But these sets are somehow constraints of how much you can take from a certain collection of goods in total. And so across all the sets where some element occurs, you can't exhaust in any of the sets the capacity. You could say that's a somewhat natural problem. I think if you just stare at set cover and think about what would be the natural dual problem, it's very hard to come up with the right definition that's both intuitive and correct. But if you do the mechanical dualization, often in hindsight, it's much easier to make sense of this problem or rewrite the problem slightly so that it becomes somewhat more intuitive. Okay, so the dual set cover problem looks like this. The constraints are essentially summing these amounts of each universe elements over a set up to some capacity or cost. How can we use this in making an approximation algorithm? What we'll do is actually not a new algorithm, but it's the same we've seen before, the greedy set cover algorithm. And if you remember from last week or so, the analysis there was this price lemma where we said, so the algorithm, again, just to remind you or make that clear again, we always pick as the next set greedily the one that gives us per element that we cover now with this set that we didn't cover before. So per new element, the least cost. That's the most cost-effective set, and that's the one that we pick, and we do that greedily. And back then we showed that there's each element is covered at a certain price, namely when it's first covered, we compute what's this price of the set we included per new element and fix that. And we showed that this price can be upper bounded because you could have, at any point in time, just taken the optimal solution to cover all that's left. Here we'll see a slightly more fine-grained analysis if you want, although the result is the same. What we'll show here first is that if you take as dual variables the price at which this element is covered, but you have to scale it down. Remember, dual fitting always has to scale down to bridge the duality gap. We scale down by hn, the harmonic number again. Then that's a dually feasible set of values for the dual variables. So intuitively, you should think of the price as the dual variable, but we can't exactly use that because it wouldn't be feasible. So why is the scaling down good enough? If you remember the dual constraint, maybe just copy this that we don't have to remember. The dual constraints are these only take as much from the good up to the capacity. And now consider some specific set. We'll have to show that this satisfies all the constraints. So let's pick an arbitrary one. And if we show that that's satisfied, that's good enough. And let's say L is the number of elements in this set. So that sum has L terms. Like at the time when we analyzed this algorithm the first time round, let's name the elements in the order they are covered by the algorithm. So whenever you include a new set, the elements that you now for the first time cover, they become the next elements in this sequence. And at the time when we cover the element EI, that's the ith element in total, we don't know how many elements from the set Sj we've already covered, but certainly at most I minus 1, because we've covered I minus 1 in total. So there must be L minus I minus 1 uncovered elements left. If you scroll back or go back in memory to last week, this is very analogous to what we did back then, but we applied it to the entire set of elements, not restricted to one set. All right, so of course that means if we take this Sj now, and we do, because that's by assumption where this EI is covered, or we could have taken that Sj now, we would cover the element EI and essentially the others in Sj at the cost of E of Sj divided by at least that many fresh elements. And so we don't know if we eventually took set Sj, but the price that we paid for EI can't have been higher because at least we could have picked Sj. Okay? And the actual set that we choose here, this Si star, is only better. Now, if you remember what that means for our variables, that's just scale down. So same thing divided by harmonic number. And now again, look at the dual constraints. So we're continuing them from there. We take the sum of the YEs in a specific set. And I'm going to rewrite that to have indices in the order at which the elements are covered. So we assume here that Sj consists of the elements EI1 up to EIL. There's some ordering of the elements, or there's some indices of the elements in this ordering, so that always works, or that always exists. So we can rewrite the sum as going through these indices, m from 1 to L. And now we insert what we know about these variables, namely this part. that's what we use. See, I'm trying to be very low on memory load today. And then you notice this this denominator is essentially just summing up the first m, or it's the reciprocals of the first m integers, so that's another harmonic number. And this comes from just going through the elements in the set here always makes this one larger, so we have to reverse the summation, but that's essentially the same as we've done back then in unit 10. And so ignore that things are reappearing below there. That's another harmonic number, the Lth one, and L is at most n, right? L is the size of the set, so it can't be more than the entire universe. So this is below 1. So we get our upper bound by the cost of the set. And that was the dual constraint. Okay, so this is all. That's why there's the end of the proof. And the sneak peek here you already had is if you do this if you show this for all the constraints, that means our scaled down y divided hn is dual feasible. And then with the chain of arguments at the beginning, the dual fitting in general, this part, copying is so much fun and it doesn't cost. You derive this part. So we're using that chain of argument and our delta is hn, so we get an hn approximation. Now you may say, amazing, we've already known that. But in a way, the algorithm, the analysis of the algorithm back then needed a bit of a magic insight that you consider this price of an element and that you somehow upper bound this. It was much more ad hoc and coming out of thin air. Whereas here, the dual constraints very, very much guide you to do the right thing. So it's maybe a bit less surprising or a bit easier to come up with the analysis in this case. A small extra benefit, but I'm not claiming this is unique to this analysis technique, is that you see you could actually have taken HL as the scaling down if you take the largest of the sets. Because for each of the constraints, we only needed HL divided HN to be at most 1. That's also true if you pick, instead of n, the largest of all the sets cardinalities. There's a slight bit better, of course, in the worst case, not that much. But set cover becomes kind of boring if there's a set that covers most of the elements. At least it's often clear whether that set should be part of the solution or not. So maybe this is, there's some beyond worst case analysis that one could do there. Another thing we can get from our duality theory here is another piece towards the another piece of evidence supporting the claim or supporting the suspicion we might have that we can't do much better for set cover. That this harmonic number is essentially the best worst case approximation ratio we should expect if we don't look at any other instance specific parameters. And so if you phrase that our approximation algorithms can be seen as relying on the integer linear program and its relaxation. So we've shown with the previous algorithm essentially that the integrality gap is at most hn, because we bounded the cost in terms of the optimal LP value. And I mean, this is, maybe I should show that here again, right? This is the bound we get in terms of the set cover we compute is hn times the optimal objective value for the LP. And that, of course, is a bound for the optimal integer linear program. But we really get a slightly stronger result here if you want, or a slightly more insightful one. So we've really shown that the integrality gap is at most hn. And maybe we can also show that it's at least hn, so that the integrality gap is a key barrier as long as you rely on algorithms that somehow use ILPs, LPs in all the ways we've seen. There won't be a way to improve. And that's indeed the case, or at least almost. There's an example that we'll construct that shows that this integrality gap is at least a constant factor times hn. And the precise thing we'll show is this, and it's exactly as you might want to read it. We will show the optimum cost of a set cover instance in the example we construct is log of n plus 1, whereas the fractional optimal is essentially constant. And so I think that example, that bad example or family of bad examples is kind of insightful in its own right. It's a clever use of linear algebra. So here it goes. We can build this for an arbitrarily large input size, but it has to be a power of 2 minus 1. So there's some L, and we can essentially use numbers of L bits, including the leading zeros. But we don't include 0, so that's important. The universe, as before, by the way, is 1 up to 2 to the L, excluding the last one, so up to 2 to the L minus 1. We'll treat these numbers, so I'll write the boldface I if I mean the vector. We can treat these numbers as a vector, which just consists of the binary digits. So if I have the number, I don't know, what's a good example? Maybe 9. I can write this as 0, 1, 1, 0. That's actually not a nice example because it's symmetric. How about we make it 11? 2 more. So you can write 11 in binary. And then I'll do the boldface 11. That means just the vector where you take the entries in order. The order is actually not relevant for what follows. Okay, but we'll identify the numbers and their vectors in the following. So the sets that we'll define as J for the same, essentially same as the universe. I don't think the 0 should be there. I think it should be 1 up to n minus 1. Is exactly all the vectors I, or all the numbers I, such that the vectors have a scalar product that is 1 modulo 2. All the vectors are binary, they're only 0, 1, so all the scalar products will be integral. And if you take modulo 2, you're just asking, is this odd or even, right? There's maybe a strange definition, but you'll see in the proof why it's useful. The cost for all the sets will be identical. So the whole thing has a lot of symmetry, which is on purpose. The size of each of these sets is exactly n plus 1/2, or maybe nicer would be to write 2 to the L. So 2 to the L minus 1. And that's also the number of sets that a specific number occurs in. And to see why that's the case, if you take any number j and look at its vector, it might be some arbitrary collection of zeros and ones. The only thing we know in general is that it is not the all 0 vector. That's why it was important to exclude the 0 here. So there's some 1, and maybe I'm looking at the last one. Doesn't matter where it is. I can take I to be an arbitrary pattern on the on all the positions except for this last one. And I can always put the last digit so that the ITJ is 1. I can always fix this. Say I'm doing 0, 1, 0, 1, just making this up arbitrarily. That's fixed. And now there's this position that I cannot fix. For this one, I have to calculate. And so you see, they have a 1 in common on the second position. This zeroes out everything else. So all that's left of this, excluding the red part, is a 1. Right? Is 1. All the others are zeros. So I have to put the red to 0 to make that a 1. If I had put a 1 here, it would be, the scalar product would be 2, which is 0 modulo 2. So it's a simple proof that no matter what J looks like, as long as it's not the all 0 vector, you can pick all but one bit arbitrarily, and you can always fix it actually in both ways. The red position decides whether it's part of Sj or it's not part of Sj. And there's perfect symmetry because these sets, the way they're defined with I and J are, you can swap them around. That's why if the size of a set is a certain quantity, the number of elements, the number of sets an element occurs in is the same quantity. Okay, so that's curious enough. Now this is enough to show that we have a very cheap fractional solution, because you can just pick a 2 out of n plus 1 fraction of all the sets. They in total will be a set cover because of this, right? The dual constraints were, sorry, the primal constraints is what we need. Is for every element, you want that the sets that are containing this element in total provide at least 1. And that's satisfied if you have that many sets and you set each to the reciprocal. And so the optimal objective value will just be n times for covering all the elements. So it's the number of sets, should be the number of sets, right? Why is this n times? I think this should be the number of sets because we're just summing up all the variables. So it's even slightly better. You get an is the number of sets in total. Oh, the number of sets in total is n. So yeah, okay, sorry, it was correct. It's the number of sets, but that is n. I confused myself with the size of the sets, but really, number of sets is for all those j. I think I confused myself here with the indices. This should be from 1 to n. It should be symmetric with the universe. But there's n of them. So we have n times the cost times the variable. And that's roughly 2 plus minus. At the same time, how many sets do we need in any actual set cover, integral set cover? That's a bit tricky to properly prove. It's kind of clear that the sets are really big. So in principle, there could be 2 that just perfectly overlap. The first covers the first half, the second covers the second half, then we'd be done. But the way they're chosen with these bit patterns, maybe you get the feeling that this is unlikely, but there's a nice formal proof. Suppose that there was a set cover that contains only k strictly less than L sets of, say, I mean, all the sets correspond to some numbers. So say these are the numbers I1 up to ik. I'm going to write these as row vectors in a matrix. So that's a k times L matrix then. It has k rows for the k numbers, and the columns are the digits. Because it's a k times L matrix, it cannot possibly have rank L. It has to have rank at most k. There's not much you can do about it. And so if you look at the null space, so a set of all vectors that if you multiply them to A, you get 0, then that's not just the all 0 vector. You get some other vector j, so that the product is 0 modulo 2, right? This is where the whole thing is also the rank, if you want. We're computing in the field F2. Now that means that J, if you look at what this matrix product is doing, matrix vector product, it multiplies vector J with each of these i's and takes the scalar product, and the outcome is supposed to be 0. That means for each of those I1 up to ik, J is not part of the set because they were defined to exactly be the ones where this scalar product is 1. And so J is not covered. Okay. So that means you have to include at least L sets. I guess L is also sufficient, but that we don't care. At least the optimum is log n plus 1, namely L. And so if you take the ratio of log n and 2, you get slightly better. This is log base 2. We wanted log base n, log base e. But then you get this result. So as long as we're doing essentially integer linear programming based tricks, we won't expect something better than this harmonic number approximation ratio for set cover in the worst case.